Hello, everyone. We are Błaz Kubiak and Krzysztof Kudrynski, and in our talk entitled Deep Learning in Computer Vision, we will be talking about deep learning in computer vision. The plan for our talk is first to get extremely excited, and we are dedicating 7 minutes, especially for that, because the world of technologies that we are all contributing to with our code simply deserves that. Within the next 17 minutes, we will truly understand the concept of convolutional neural networks by a quick, but I hope very interesting, Python coding session. And for the rest of the talk, we will go through our own challenging real-life project where we will hopefully see amazing possibilities of modern AI, so amazing that you might even get scared, for which we especially dedicate the last minute of our talk. Okay, let's start with science fiction. A classic from 1982. In this scene, Harrison Ford is analyzing a photo using a hyper-mega computer. It is year 2019, so it can obviously zoom and enhance beyond any physical reason, but that's not the end. This computer can even look around the corners. What a technology. This film is a classic. It's great to watch, and although the film was shot when I was still very young, even then, I could feel this something is not right. And I'm sure that everyone here, if you watch this film during this scene, you felt this strange embarrassment, maybe. If you did, well, we still haven't reached 2019, and the world of science already says we are actually able to reconstruct details that seemingly could not have been captured by the camera due to its physical limitations. But okay. We can believe in zoom and enhance, but seeing around the corner, come on. The end of 2017, guys from MIT and Google published a method in which using a camera, you can trace objects around the corner. It is actually done by looking at indirect reflections, and you can trace these objects with centimeter level accuracy. Well, isn't it amazing? I hope it is. Maybe it doesn't mean that we can look at the face of the android lady around the corner, but it is not 2019 yet. This technology was developed by people from blood and bones, just like us. The next scene, EagleEye, the film from 2008, where a super intelligent computer is trying to take control over the world. People try to hide from it in a soundproof room, switch off everything, hide in the shade, but the machine reads their conversation from the vibrations of water. 2016, guys from Microsoft, Autobahn, and MIT publish a technology which does even better than that. Now you will see a video of a flower listening to music. Not very action-packed, but it's actually a video. And now, it's the same video again, but with the music reconstructed from the micro vibrations of pixels in this video of the flower hearing this sound. Amazing? This technology was developed by people from blood and bones, just like us. Finally, awaited by everyone in this room, David Hasselhoff and his talking car. Well, it talks. That's not too extraordinary now. It knows what it is talking about. And it can describe its environment better than Brian Getz can describe the new Java features. Fiction? 2015, a machine is able to semantically segment an image and generate grammatically correct sentence describing it. All these images descriptions were generated by a machine. Is it impressive? If this is impressive for you, you are not ready for the next slide. Also 2015, Generative adversarial network learns to draw photorealistic images based on what you say to it. So no one has ever made this photo. This bird does not even exist. Similarly to any of these. This is how a machine learned to imagine a sentence. And this technology was developed by people from blood and bones, just like us. But let's not forget that our car can actually drive itself. Impossible? Well, you probably are aware of how much is going on in this field. For example, in TomTom, since 2015, self-driving car technologies are being developed extensively to enable cars hit roads globally. And these technologies were developed by people from blood and bones, but not like us. I could tell you exactly who wrote these patents, but ladies and gentlemen, we are too shy. The cars drive by themselves, robots do their job on their own, machines learn to see, machines learn to fly. We are living in amazing times. All these technologies are at our hand and we can participate in their development. And I am sure you are getting thrills to start this amazing adventure by classifying cats and dogs. No, we won't do that, it's just a joke. But to get the fundamentals, we will start with something pretty easy, like classifying faces into glass carriers and normal people. Do we need AI for that? Maybe, but let's first start to think about this problem in a traditional step-by-step solution, handcrafted algorithm. Let's just do it. So first, we will find edges by applying proper horizontal and vertical filters to the image. We will do it by convolution or correlation, which is simply creating a small mask and sliding it across the image and multiplying and summing all of the things from the mask and below from the image. We'll sum it, multiply, sum it, and we have our result. Is there anything in the world easier than that? No, there isn't. But however trivial and however obvious, convolution is the most important operation of today's talk. So now we have our result. Let's zoom out a little bit to look at our image at further perspective, but we will not do this by typical resizing, because with typical interpolation during resizing, we would lose a lot of nice edges that we have just detected. And to make sure we are not losing these edges, which you can see very nice here, there is no, they are very sharp. During resizing, let's always keep the maximum value pixel in the result. This is called max pooling. Is there anything in the world easier than that? No, there isn't. But however trivial and however obvious, max pooling is the most important operation of our today's talk. Okay, at that scale, let's create a frame filter. Well, a frame is just a rectangle shape, more or less, consisting of vertical and horizontal edges. So we do it, we convolve again, and we zoom out. And now we would like to detect the glasses as two frames. So because the frames are already detected, we'll detect just two dots. To detect two dots, we write our filter and convolve, zoom out, and now we are almost at the end. We can easily classify our result. So if the middle pixels are much brighter than all around, then we probably detect glasses. In this case, it is true. The response from the mid is much greater than from all around. So we have 97%, we are sure that these are glasses. Now, in code, an image is a matrix. And many multidimensional, multi-channel images is a tensor. here n by 200 by 180 by 3. If we design a filter, it needs to be a 3-channel filter because we have a 3-channel image at the input. But now, because correlation and convolution will just multiply and sum everything from all of the channels at the output, we will have just n one-dimensional images. But we can have more filters, we can design more filters to detect more features, and then each result would fall into another channel of our image. Details now are not very important. What is important is that, in fact, we are designing a graph of Tensorflow. And actually, there is a library with that name, designed by a company doing quite well on the market at the moment. So there is no reason not to use it. So we will use Tensorflow today. We will first create an empty graph and then use a session to feed the data placeholders with our images from the disk. In fact, for performance reasons, even loading the data can be part of our graph. Okay, but now I am seeing this question in your eyes. We did a lot of manual stuff. We manually created our filters. There's a lot of work. Where is this whole artificial intelligence? Nowhere. But beware, it is coming, and in case you are planning to have a short sleep now, I am telling you it will arrive very suddenly. So let's start our implementation quickly. We need Tensorflow, NumPy, OpenCV, and OS. We will build the graph, we will read the data, we will run the graph, and we will show the results. In our graph, we put a placeholder for input data. This will be 200 by 180 pixel, one-channel images. We don't know how many yet, hence the none. And we'll load the labels for each image, because during development, we have the images labeled, whether they have glasses or they are normal people. We will soon prepare a class, let's now call it filters, which will have separate method to create and return a filter that we need. So one will be for edges, one will be for frames, one will be for glasses, and one for final classification. Okay, now the graph is very simple. We will first take our data from the placeholder, we will filter it, zoom out, as we discussed before. First we will detect glasses and zoom out 10 times. Then we'll detect frames, zoom out just a little bit more. And then we will detect glasses, zoom out a little bit more. And finally, we will classify. Now in the end, we have some results. So let's calculate some metrics, how well we did on more examples versus the labels. Metrics are very, very useful. We want to check how we are doing in detecting all kinds of glasses in various circumstances. For example, a perfect detector of John Lennon's glasses on the cover of Imagine album is not good enough, especially if it was trained on John Lennon's glasses on the cover of Imagine album. To avoid such disappointment in production, let's calculate accuracy and cost for some more examples. So accuracy is simply the percentage of correct predictions, where a prediction can be just right or wrong. Now, the cost is something more. It is defined as a continuous function. For example, detecting glasses for 95% for this lady seems correct. So from the perspective of precision, from accuracy, it will be just correct. But a well-justified question is, where did the 3% go? The 3% is transformed into a loss. In another example, for some reason, our detector was really confused, and while it was still correct, the loss here was much greater than for the lady. And finally, when our detector sees Harry Potter, it is 99% sure he has glasses, and however sympathetic we could be for this decision, the loss is huge and unforgivable. So we have our metrics defined as accuracy and cost, so we need to load the data. Let's create a class for that. We have photos in 2 folders. 0 are people with healthy, typical eyes, and 1 is the elite with the glasses. Let's create a method which will load the data. We will work on several photos at once in batches, but as mentioned before, we will perform the actual loading of images in a session. Let's create it, and finally, okay, we would like to display the results soon of running our session on our loaded data, which we put in place of the placeholders. And with the same data, first we will just print the metrics, as you can see, and then also display some visual results. And okay, now we would need about an hour or so to implement all that stuff. There's a lot of custom-made functions, as you can see, not implemented. But most of these things are like displaying images or reading files from the disk is really trivial. So it would be too much of a waste of your time if we go through all of the code. So we'll just do it very, very quickly now. Of course, we will share the code. But it's much better, obviously, if you just follow it while we are trying to write it. But it's not our aim that you understand now every line being typed. We are showing the full coding session so that you have the impression that the whole experiment is within reach of writing in 1 or 2 hours of coding. And during this talk, we will focus only on the most important parts, which will start now. So we have all the helper functions and placeholders for some methods defined, so let's focus on the problem. And first, we need to implement the filter and zoom out. We will filter using convolution, which we have in Tensorflow. We will filter and shift our mask 1 by 1 and pad the result so that it is the same size as the input. Now let's implement the mysterious filter. In fact, 4 filters, 3 by 3. Now, what is a filter? A filter is just a matrix, a small matrix, and we want it to detect edges. What is the edge in the image? It's just the change of intensity of pixels in the image. So, for example, going from 2 to 1 to 0 is a change of intensity of pixels. That's an edge. So we are defining a left edge by going from 2 to 1 to 0, and we will try to correlate it with the image, and this way we will filter out only the left edges. Similarly, the right filter is just a flip of the left filter, and top and bottom edges are just transpose of the left filter and flipped transpose, obviously. So let's see. Let's run and see the results. Nice. So we have some 2 images of ladies. We have our 4 filters, left, right, top, and bottom. And we have the results for both ladies, a 4-channel result. In every channel, we have the detection of left edge, right edge, top edge, and bottom edge. The results are nice, but there is something which we probably don't like. If you look carefully, the first 2 results are very similar to each other, and the second 2 are also very similar to each other. In fact, they are symmetric. Because obviously, if you are trying to detect a left edge, it's a negative of the right edge, so the right edge will appear in the negative part of the left edge detection, and similarly, for the right edge, the left edge will be seen as the negative of the right edge. So the 2 first are symmetric, similarly for the last 2. And we don't want that. We want every filter to be unique to detect what it wants to detect. So what we don't want is the negative part, in fact. So we can get rid of the negative part. And the question for you, how you would call a function which cuts off the negative part? Probably cut off negative, probably negative to 0. But respect to the guy who came up with the super intuitive name rectifying linear unit. In short, ReLU. And that's not the end. The world of science went crazy. This is just 0 and x. And the world of science went crazy. ReLU is believed to be the greatest breakthrough in the world of artificial intelligence. You can even see it penetrating into the world of pop culture and art. Is there anything in the world easier than that? No, there isn't. But however trivial and however obvious, ReLU is the most important operation of today's lecture. Okay, it's also implemented in Tensorflow. So let's add it and show the results. And now it's much better because we can only see detection of edges uniquely for each of the image. Beautiful. So now let's zoom out using max pooling. We will zoom out by zoom times with a zoom stride and a traditional padding, and then we will show the results. And now, well, after detecting edges, we set zoom to 10 times, if you remember, which is quite aggressive. And you can see this effect. In Poland, we have a perfect name for that, pixeloza, which is maybe a bit extreme here, you can see. But with such resolution, the frame of a single ocular can be detected with a very small filter, because now it only occupies like 5 by 5 pixels in our resulting image. So we can have a very small and efficient 5 by 5 filter to detect it. So this will be a filter working on 4 channels, and because in the first 2 channels we detected left and right edge, and in the last 2 top and bottom horizontal edges, we can create our typical frame detector as a rectangle and closed by vertical left and right edge from left and right, and horizontal edges from top and bottom. So let's run. We see the results. There are beautiful 2 frames detected for the first lady as pair of bright pixels separated by 2 other pixels. So now to detect the glasses is a no-brainer. We just need to detect 2 dots next to each other. Very simple. So let's get dirty with our implementation. Okay, 2 dots, 1 here, 1 here, ready. And in the result, we will see a beautiful shining dot somewhere between the eyes of the young lady with glasses, and nothing for the second lady. After a few lines of trivial classification code, we arrive at the final result. We finish with just 2 pixels per image corresponding to 2 classes. So the top lady has glasses, so the corresponding glasses pixel, right pixel, is more white. While the lady at the bottom, she has no glasses, so the pixel with no glasses on the left shines a little bit more, which is a great result. Adding a few more guys. So, perfect. First glasses found, second found, and now third and fourth, we are reached by the brutal truth about the world, which says that not all glasses look like windows. And in all honesty, we might even fail with John Lennon. It's just, imagine there's no heaven. As you can see, for more difficult cases, we were just wrong. So to sum up our status at the moment, we design a network composed of layers, of just 3 operations. Very simple, but very important. Convolution, ReLU, and maxpool. And for each convolution, we manually crafted some filters. We did it by hand. We just crafted it. And now you can see all of them at the slide. Our solution worked well in happy cases, but in general, it didn't work well. So we could play with these filters. We could improve them a little bit, tune them to detect more difficult cases, check it versus another examples, and as a result, improve the accuracy and cost of our solution. We could do that, but we will not. Instead, we will put random values to our filters. And then we will let the machine to optimize them for us by showing it more and more examples. And we will do it by adding one line of code. So, ladies and gentlemen, it is arriving. They tried to capture this moment in the Terminator. They tried in the Matrix. But it is you, ladies and gentlemen, staring, and this line of code being typed in, it is you witnessing the death of a handcrafted human solution and the birth of artificial intelligence. Yes, minimization of the cost function. Artificial intelligence is basically just minimization of the cost function. But is it disappointing? If you expected supernatural phenomena and the touch of the human wand, yes, your feelings might just got hurt. But on the other hand, when you realize what we can achieve with such theoretical simplicity, well, it just blows your mind, I think. In our case, while writing this code, even our operating system got intimidated by the emerging artificial intelligence, and it also asked for an update. Coincidence? I don't think so. But anyway, after a few technicalities, your convolutional network starts from some random values and it starts to shape itself step by step. By adding more and more examples, it is shaping itself so that the filters are optimal to do their job. By seeing more and more labeled images, it is doing the job we did before manually. Here we will arrive at about 80% of accuracy, which is not very good, but it is a very small network. But now, when we don't need to manually craft all the filters, we can make it bigger. Because why not? And then we can observe how the machine crystallizes its solution so that it finally detects our glasses with a perfect precision and accuracy. So, is deep learning just about stacking more layers as the complexity of the problem rises? Not exactly, because every layer comes with responsibility and risk. Deep networks are hard to train because they are trained by backpropagation, so from the back to the first layers. And because of that, the gradient can become unstable. For example, it can vanish, and then the early layers will learn very slowly or not learn at all, or it can even explode. And as this field of science evolves, new ways to solve these problems arise from traditional techniques like smart initialization of weights, regularization, gradient clipping, and design of new activation functions, up to solutions that are so clever that you might get thrills when you read a scientific paper. For example, GoogleNet was so deep that it could not be trained by standard optimization of the loss at the end. So, to make the earlier layers actually learn something, auxiliary small networks were attached in between the layers, designed in such a way that they all learn the same thing and the cost is shared. This way, The small network at the beginning will try to detect the same stuff as the big network. Of course, it will fail because it's too small for such a big problem, but at least it will try to go in the right direction, so that then the next network and the next network will be able to learn much quickly what it's going to learn. It's an amazing idea. Microsoft, in their ultra-deep network, introduced residual connections so that successive features are put in the context of previous layers. And now there is additional path so that the gradient can backpropagate more easily. Now we could talk hours about these amazing ideas and new solutions emerging every day. Probably at this moment someone is writing a paper that will change the state of the art tomorrow. But what seems to never change is the fact that to properly train anything, we need loads of data. Sometimes hundreds of examples, sometimes thousands, sometimes millions. So, how about the newest science fiction from 2018, The Expanse, Distant Future? A group of main characters is looking for a missing girl, having just single photo. Will the algorithm be able to find the girl having just one training sample? Of course it will. Impossible? 2018, 15th of November, Belgium, the Devoxx conference. Krzysztof Kudrynski and Błaz Kubiak will now talk about their project.
Hello, everyone. So, great introduction of Krzysztof. Now we are going to move to our project, our practical project. So, let's think about you're watching the movie and there are lots of faces, a lot of characters, but in fact only one character is important. So, you are looking all scenes where Chuck Norris appears. So, how would you approach to such problem? Should we turn this task into a classification problem? Maybe yes, but then we would have to gather big data set of Chuck Norris faces and maybe another faces to have a separate class for that. And we have to train network, and it would work only for Chuck Norris, not for anybody else. So maybe another solution is an option. So let's think what is our goal. We have to say if two faces belongs to the same person or belongs to the two different persons. And actually there is specialized type of networks, deep neural networks, that works for especially that purpose. And the normal neural network at the end as output has label, and this network has no label but has feature vector. So when we feed that network with faces, we have feature vectors at the end. But these are not random feature vectors. They should be really well designed to distinguish these two persons. Which means that if we calculate Euclidean distance between these vectors, it should be, for two different persons, should be maximized, and for faces of the same person should be minimized. So, normal network, we train minimizing distance between actual output of the network and a label that we have in dataset. And this network we are training in different way. So we minimize this function, which means that this component minimize the distance between feature vectors of the same person, and maximize distance for two different persons. These kind of networks are quite tricky to train. Usually they are quite deep, so we would need a lot of computation power. There are nice papers about that. They introduce some nice tricks that can be used. But today I will show something different, something simpler, something that we can do during this talk. So we'll use existing network that was trained for some task. In this case, it is a network trained for face recognition. But we will remove classification part, which means that at the end we have feature vector. So when we feed the network with faces, we have feature vectors, we can compare them. But the problem with these feature vectors are that the network was not trained to maximize distance between these feature vectors. That's why we won't use simple Euclidean distance between these feature vectors, but we do the trick. So we subtract these feature vectors, and we train our own very small, fully connected neural network, just 3 layers, to say yes or no, if these feature vectors belongs to represent the face of the same person or not. So how we train that network? We get the data set of faces. This is a well-known data set of celebrities. Can be freely downloaded from web page. There's a few thousand of characters. Most of them have a few samples of a few faces, a few pictures of face. And when we train our very small neural network, we will feed the network, feed this big network with 2 faces of the same person, take the feature vectors at the end, feed our new network, and for the same person, we put label 1, yes. And on the other hand, if we have we take 2 different faces, we say no. It's very simple, and we can do that now. We'll use Keras framework. If you have a few minutes to play with machine learning, it is, I think, the easiest framework that exists. It is, in fact, wrapper over Tensorflow. But to prepare network, you just need a few lines of code. So you just define the sequential model, add a few layers. You set optimizer Adam, which is most popular optimizer used for neural networks. You compile the network and train the model. Now let's go from slideware to software. So this demo time. So now we are starting training. Okay, now it's initializing. What is nice about Keras, it comes with whole, let's say, communication about how the training is going. So you see that what is going with accuracy. You don't have to add anything else. Just these few lines of code, and you see how training is going. What is also nice, because Keras is wrapper over Tensorflow, there are some additional callbacks that you can add, especially for Tensorflow. And if you add that, you can see a very nice tool which is called Stencilboard. It comes with Tensorflow, and I will run it now. So when we run the Keras with Tensorflow callback, it writes special logs, and then we can open Tensorboard. It is very basic service that runs on your computer and reads the logs. And when it started, we can go to the browser and see what is going on with your network. I didn't add any special characteristic that that shows here. It's only accuracy and loss, but it shows a general idea how can be used for watching how your training is going on. Okay, let's see if it is finishing. I think it should finish within a few iterations. when we finish, we'll try to run this network in real scenario. So we'll take the picture of person, and we'll see if we show, we will compare with another faces. It will be the network tell us it is the same person or it is different person. Give me a second. So I think
yeah, we will need a volunteer probably to share their face. We have 75 pages of GDPR to be signed later for photographing our face. Let's do it just after. Don't worry, we have everything. So anyone? It's better closer somewhere here to. Okay. Oh, you can sit down. You can sit down. Okay. It's a demo, so it never works, but okay. It's okay?
let's see.
Oh, it's very blurry, but
Well, I think we should try again.
sorry. It's the light here is not where we trained it.
Exactly. Come on.
Why? Man, you have no face. Another one. No. Can we try? Can we try? Can you stand up for a second? And maybe to the light, it will be easier. Okay. Sorry for that. Are you doing that or no?
Give me a second.
Oh man.
Application don't want to die.
I think it's because of the bird. You know. Are you ready?
No.
How many minutes? 8 minutes. Okay.
Okay. Try to stabilize. Oh, now
Yes.
should be better.
Just wait. Yeah. Now
Okay.
we will go through some faces. You can see the red showing that they detect face. But hopefully, if I send on the light, only this
Yes.
face is green.
Wow.
You can imagine what we can do with this technology.
Actually, when we came with this idea to Stefan, he told us that he has idea to have an application to find in all Devoxx pictures that he has in his the library. It is like probably millions of pictures. He wants to, for example, find all pictures for particular person to put somewhere in the schedule or whatever, and we try to do, let's say,
A prototype of a
application.
prototype.
Yes, prototype of prototype. So we'll run now. Okay, maybe short introduction. So I did like a few thousand of pictures from Devoxx. It looks like this. So there's a few folders, and I process all this data with this face recognition network. I gather feature vectors and put it in NumPy array and save it in the folder. And also prepared another file with boxes to know where the boxes of particular persons, and I have also the mapping file that shows that describes for every picture where it starts in this big NumPy array, where features starts and how many boxes are assigned to a particular person. So when we load up our application, there are two tabs. In first tab, we saw the sample images with persons that we are going to look for. And on the right side, we'll see the result. Now it's empty. And when I click on particular person, it will go through all these folders, read these metadata that I prepared before, and we'll use this small neural network to compare this face with all the faces that are in our library, let's say. So let's see how it works for this person. It's not, as I said, it's a beta version, but we'll see. Okay, process done. Let's see. Okay, there are some correct answers, some not. Maybe let's try with Stefan. Come on, come on. Yeah, so we have a few hits. However, it's not perfect. We are quite happy that we prepared that. Yeah.
Okay, so we will come back to very quickly to the presentation. Just to end. Does anyone know what is that? The top cross is what the person is looking at, and the cross below is what the machine generated by analyzing their brain activity. More examples here. To me, it's a bit disturbing. Maybe it is not a fully deserved reading in your mind yet, but that's clearly a first step. It is well documented in the literature, tested, and it is working. Soon the machine will be able to read your minds like that. It is going to learn any task you give to it, and it will always do so by optimizing the cost function. So whether you assign it to save the planet or to win a board game, make sure to double check two things. First is to set the cost of human life to infinity, and then check if infinity is properly implemented in your machine. Thank you very much.